IQS current. This is our IQS current. And in FOC, we will take IDS current reference as 0. IQS reference is produced using a speed law, whereas IDS reference is 0. So this is IDS reference, which is 0. Then IQS reference is 1. After these two signals, this is a current error, or you can say current hysteresis based FOC. In FOC there are many type of FOCs. The method which I am going to explain is current hysteresis based FOC, which is very easy compared to other FOCs. For doing this FOC, we don't need any parameters optimization. Simply by controlling this ID and IQ, it is possible to control the speed of the motor. So ID, IQ, initial stage, for this particular experiment, we need only sensor circuit. Only if we have two current sensors, it is possible to implement FOC. So the two current sensors, we will get IA and IB. And we know this particular control will work in a balancing condition. Under balancing condition, we know that IAS plus IBS plus ICS is 0. Then ICS will become minus of IAS plus IBS. So just by sensing IAS and IBS, we can estimate ICS without using the third sensor, so that we can reduce the cost of the third sensor. And IDS, IQS references, we can convert these references to IA star, IB star, IC star. But directly we can convert it is possible using inverse class transformation. But here we are doing with the help of step by step. Like first we will do Park inverse, then we can get I alpha star and I beta star. Then here if we apply Clark inverse, then we will be getting IA star, IB star and IC star. These are the reference currents in the natural field. These reference currents need to be compared with the actually sensed currents, which are IA and IB, which are sensed using the current sensors. But IC is estimated. Yes, all sensors will be estimated. So this we will give IAS here for comparison. Similarly, IBS star and IBS, actual IBS are compared. Then you will get related to second phase, B phase, here current error will be given. So whatever current errors we are getting here, that current errors are given to, in MATLAB you can see there is a relay operator. You can see a relay operator. In this relay operator, we can limit this particular current error within that band. That band you can choose randomly initially for testing. So that band will be like step on time. On time will be like 0.0, half time minus 0.0. That means within that range 0.0 to minus 0.0, we will be changing the constant. So if it is crossing this value, we will turn on the switch. If it is trying to go below this value, we will turn off the switch. So based on that, switchings are given at 1, 0. That I will show you how to take in the relay. Based on that, 1, 0 switching states are produced. If after getting the 1, 0 switching states, these switching states are directly applied onto the inverter. Then inverter will give us required voltages as per the closed loop. So that required voltages will get applied on the motor, and motor will run at the particular speed. Depending on our kV and Ki value, slowly machine speed will reach to actual speed. Actual speed reach to commanded speed. We can say this is demanded speed or commanded speed, or the speed at which we want to run desired speed. So it will reach to the desired speed. So this is the logic. For this we need Park inverse and Clark inverse. Before going for that Park inverse, these equations are already explained it. But Park inverse matrix is this one, which is cos theta, theta is nothing but the position, minus sin theta, cos theta. Actual path transformation, it will have cos theta, sin theta, minus will come here, then cos theta. Actual path. It is inverse path. So inverse Clark transformation, actual Clark transformation is this one. In magnitude invariant time, I am telling 2 by 3 times of 1 cos 0, minus 1 by 2, minus 1 by 2, 0, 3 by 2, minus 3 by 2. This last column, if you want to use for zero sequence, you can use, but it is not required. Anyways, based on the system, It's 1 by 2, 1 by 2, 1 by 2. 1 by 2 for magnitude invariant. If it is power invariant condition, here it will become root 2 by 3. This factor will become 1 by 2. Yes. So here this transformation we will take for I alpha, I beta and I naught. This is like IA, IB, IC. But here in this case we need an inverse clap. Inverse clap means we need IA star, IB star, IC star from I alpha star, I beta star. So if we do inverse of this matrix, first we will take this factor to that side, it will become 3 by 2. Then inverse of this particular matrix into I alpha, I beta. We can if you simplify this, solve this equation, you will get IA star is equal to I alpha, IB star equal to minus 1 by 2 times I alpha plus root 3 by 2 times I beta. And one more I star is I alpha, sorry, IB star, IC star will become, here we will get negatives. This you can get from the inverse of the matrix. So these equations I will be using minus 1 by 2, 3 by 2. So minus 1 by 2 is minus 0.4, 3 by 2 is 0.8. So this equation we will use here, and this equation I will use from the directly we will get I star, I star, I star. Comparing with the actual currents, we will get current error. Current error is given to relay. Relay will produce 107. Several states are applied. So this is logic, but to implement this logic, we need sensors. So step by step I will explain, sir. First we can discuss about voltage sensor. See, voltage sensor, anyways for FOC it is not required, but I try to give idea about this. So we are using a sensor parts
for each header. So it will go till 190 because this microcontroller GPIO will 190. But just for this model we are using 2 GPIO. So we will assign at default GPIO is 2. Let's assign GPIO 1 and GPIO 2. Nothing special, just normal as name applies. So when you select GPIO 1, you have to deselect for the first one, that is the default. So now here there are two options, GPIO 1, and if you select, it will also show you toggle. So what toggle does is when you it's at operation, it will stay the same instead of going to on. So we don't want that. When we provide off signal, so it should be on for zero. So that's why we are not selecting the toggle. So we click OK. And we'll take it as zero period. Otherwise, you know how we have done the signal. This is already the solution that is done that I was showing you. So GPI, this one I selected. GPI 1 I selected here. Here I selected GPI 2. That is one we will show at 25% bit cycle. The other one is complete opposite. Yeah, so not signal is opposite. So in order to connect MATLAB, just on this pin will be already there in this user. Once you connect, please the lights will on. Now the second thing is we need to connect oscilloscope, the DSP to check the wave. So one thing is that here you can see ground is written here. So this port is on the right hand side. This ground, you have to connect the ground with the black of the oscilloscope port, and the other one will connect to the positive one. Right. So according to GPIO 1 is at 39 and GPIO 2 is at 38. So GPIO 2 is at 38, GPIO 1 is at 39. Ground is already written here, so that doesn't have a number. Ground. Just if you check first, check from ground to that. press here, then you have to set up. Automatically during installation itself, once the installation is completed, click on install. Manage బదులు install అని ఇస్తుంది.
ఇన్స్టాల్ చేయకపోతే మేనేజ్మెంట్ కాపీ ఇన్స్టాల్ అయిపోతే తర్వాత ఇన్స్టాల్
just check whether that version is
It will pop up and configure. So once it is installed, we have to configure it. For configuration, we have to use suppose accidentally close it. If you want, you can take screenshots. These steps you want. Take the screenshot. First one. This window will be open. Take a photo. Okay. Then you have to select which color we have to install. Yeah. Yes. We select the one. Okay. Now we have to select which is available. This T07X. Again you can install. Suppose if you are using other process, then you can select only one because we are using that. We just push it. T07X. That is not. Once you type Z2000 setup, this will load. It will direct us for installing third-party software. These are the steps. You already installed one, right? But in your laptop, it will not be installed. Okay, here directly, when it not installed, third-party tool for interfacing the app with the DSP. For that, you require code generation tools. Those code generation tools are the install. Okay, I'll share on document. Right? For which matter version you require which software. Suppose you are using the earlier versions. So what is the compatibility that you can compatibility and share that. So mine it is version is 22.6. TIC 2000 code generation because we are not generating code. MATLAB will generate code. For generating code, we will use this third-party software. So you have to install.
So for example, if we are not uninstalled, it is installed, it will show installed.
Install with low.
If we click install, versions will come. In that we need to select the
Yeah,
version.
I can reinstall also. Suppose they are not working properly, earlier versions are there. You can click on the reinstall. Okay? So if you click on the install, they will automatically install. So once they are installed, after installation, you have to go back and you have to check. So once they are installed, you will get installed. Okay? Then click on next. show the generation of the pulses. Right? So same thing. According to the model, now I just change the model to sine triangle. Once for black is for round. Red is for GPIO 180. GPIO 1. Now what we do? Same thing. One thing, make sure that stop time should be infinity. I can keep infinity so it will take some time. This is sine triangle. Yeah, sine triangle. Backward. Once sample time are taken, so I have taken frequency of 2.5. So if you comparison with a triangle, then stop time will just keep it as infinity. Go for the same rate as
In models, it will allow to do any settings like fixed steps and
so yeah, here they are using fixed step, discrete only, discrete software, and then accordingly you need to check what the step time is. So for this, I think so it was 10 e minus 6 minus 10 minus step time.
what is the switching frequency of the
1.25 kilos.
so that is the steady state.
Yeah. Once built, it will show that build is completely successful. Even if the build is like if you want to check, now you can see at different sine. Yeah, so pulse width is changing as per the sine triangle. Sine.
So frequency is
So accordingly, you see this sine triangle as comparing with the normal sine. So these are the three experiments normal. So how the pulses are generated, how we can link them
3000 pulses per 1 revolution also. According to the number of pulses per revolution, this particular signal will change for the incremental input. According to that, our control logic also will vary, our scaling also will vary. So for 1024 pulse, so that means for every revolution, it will produce 1024 pulses. So if you see here pulses, this kind of pulses, 1024 pulses will come in one revolution. Inside there is a disk, and there is a whole type of arrangement where they will send some light kind of signal. So based on that, how many times it is hitting, they will calculate the number. If you want to study deep, you can go to this. Then based on this logic only, it is possible to find the speed from the input. So for this particular setup, we don't need this three signals, complementary signals. Even for the DSP also, this complement is coming from only A, B, Z, then VDC and ground points. On the CLP panel of DSP, there are points like this. This is nothing but INC1, INC2, INC1, INC2, port of the CLP panel, which is connected to the controller. On that, you will be having three points like this. Here, for first point, you have to provide VDC. Then second signal is your A. After giving second signal, you have to leave one pin. This signal will be B. You have to leave again one pin. This signal will be Z. Then again you leave one pin. Finally, there is only one pin. This is dot. So in this fashion, you have to connect it to the CLP panel. So when you connect it like this, the CLP panel will receive the signal. What signal it is receiving means to access that particular encoder, there are certain blocks in the method library, like integrated library of DSpace and man. So that will give delta position, and incremental delta position. These two output signals. Out of these two outputs, this output is used for sensing the signal. So from this output, we will get delta theta, delta position. Usually theta will have a units of degrees or radian. But this particular delta theta will come as number of pulses. It will give a number. Out of this 1024, some 1000 will come, some 750 will come. According to that, we have to find out what is the speed and the speed. Yes. So this one, this particular delta, we need to convert it to speed. So relation for the speed and position is omega equal to d theta by dt, which is nothing but delta theta by delta. And this particular sensing will happen every sample time. For the logic, what sample time is. So within that sample time, that sensing will happen. So this delta t will become Ts, delta theta goes from S our model sample time as a configuration parameter, we have to set this. So delta theta by Ts equal. Then this delta theta by Ts, directly we cannot claim it as a speed. Reason is delta theta is coming as a number. First we need to convert it into radian. To convert it into radian, we will multiply with 2 pi. So it will go to radian. Like we have this logic here for 1 revolution 1024 means 1 revolution means nothing but 2 pi radian means 1024 pulses. So for getting 1 pulse, how much we need means 2 pi by 1024, like that. So 2 pi by 1024, here we are multiplying with 2 pi. By Ts is always there. But even though we are multiplying with 2 pi, the number which is coming from the encoder will not get cancelled. So to cancel out that number, we have to divide it with 10. So 2 pi by 1024 times Ts multiplied. Put this delta theta segment. It will give you omega. But this particular omega, it is not in RPM, it is not in electrical radian per second. It is based on the angle which is happening inside the incremental encoder. It is a mechanical angle. That particular point. So this is your speed omega m, which is nothing but mechanical radian per second. So mechanical radian per second need to be converted to critical speed anyways conversion. Direct conversion